All right. All right. So today we'll talk about the thermodynamics of carbon capture, which it's more exciting than it sounds. And then we will also maybe time permitting, we'll get to talking about different carbon capture technologies. So here's the basic premise. So we've got increasing carbon dioxide levels in the atmosphere, and as we saw on Friday, these are increasing more rapidly than the natural feedback processes can account for on Earth as a result of basically burning all these fossil fuels. So part of the solution for net zero carbon emissions has to include some means of either removing the CO2 that's already in the atmosphere or preventing the release of that CO2 to begin with. And those are kind of two different technologies that we can look at. But you can really think of it as if you can build a giant vacuum that sucks up all the carbon dioxide, then that's kind of the system we're going for here. All right, so there's two basic methods of doing this. So one of them is to capture the CO2 at its point of generation. This is often referred to as point source carbon capture. And this would be things like installing some type of an amine-based scrubber on the smokestack from a power plant, okay? And we'll talk about ways of doing that. The other one is capturing it from the ambient air. This is often referred to as direct air capture. And this is often contrasted with capture at its point of generation by calling it carbon removal. So what you see out there a lot is that when you're looking at capturing it from a power plant, for example, that's called carbon capture. And when you're looking at removing it just from the ambient atmosphere, that's called carbon removal. So there's a little bit of nomenclature that is, the distinction is, maybe not as important as you might think it is, but at least just knowing what the nomenclature is very important. Okay, so that's the general term. Now let's talk about what is actually required to make carbon capture and carbon removal actually happen. So what we're doing when we capture carbon dioxide from either from the flue gas at a power plant or from the air is that we are separating the CO2 from the rest of the molecules, okay? And so a really simple way of thinking about this is let's imagine that I've got some mixture of two gases. One of them is blue, one of them is yellow, okay? And so initially they're going to be mixed together, assuming they're completely well mixed, they'll be randomly distributed. And what we're doing is we are changing the distribution of molecules such that we've got one gas here on one side and another gas here on the other side. Okay, now let me see how well I explained thermodynamics a couple of weeks ago. Which one of these cases is going to have the higher entropy, the greater degree of disorder? Okay, who thinks it's the one on the left? And who thinks it's the one on the right? Okay, great. So that is absolutely correct. This is a more disordered system than this one. And so to decrease the entropy, we are going to have to do some work on this system. And the amount by which we decrease the entropy is going to dictate how much work we actually have to do on the system. Okay, so the other question is, can this process happen spontaneously? And the answer is no, you can't spontaneously have a reduction in entropy because of the second law of thermodynamics. And we already figured out which one of these has lower entropy, so we need to do some work on the system. So here's how we're going to design our idealized separation scheme. Okay, so we've got some input here, which is a mixture of carbon dioxide and other stuff. So one way of thinking about this could be the flue gas from a power plant, okay? Now, it's got a certain flux, we're going to call that N, and that is in moles per second. And then we have a mole fraction of the CO2 in that stream. So we have a total number of gas moles, and then the mole fraction of CO2 is X, okay? Then it goes through some kind of a magic box, and we'll talk about what goes into that magic box later on, but let's just imagine that something happens in there that separates the CO2 from the rest of the gases. And then what comes out the other side are two different streams. So one of them is the captured stream. In an ideal case, this would be 100% CO2. It's usually not, just because of inefficiencies in our magic box. So that's going to have some flux, and it will have some mole fraction of CO2, which we hope is as close to 100% as possible. And then the exhaust stream will have some exhaust flux, and then the mole fraction of CO2 in the exhaust hopefully will be as close to zero as possible. Now, because what goes on in this box involves a reduction in entropy, there has to be some work done here. So maybe we'll power this by a hamster on a wheel. Maybe we'll use something else to power this. In fact, we'll talk about the different ways we have of powering these systems. But that's what goes in there. So this is a very, very generic separation scheme in a thermodynamic sense. So what we're going to do is we're going to define the amount of work that you have to put into this system to separate the gases. Okay, so just some basic thermodynamics. So back to what we did in Unit 1. So we're changing the energy of the system by doing either heat transfer or doing work on the system, right? So that's first law of thermodynamics. And we can separate out the change in energy to change in internal energy, potential energy, and kinetic energy. And that is equal to the sum of the heat transfer plus the shaft work minus the PV work, okay? So that's general. Now we'll keep this isothermal. And so that means that there's no change in internal energy. We'll also assume that this is a stationary system that's not accelerating and it's not changing its position with respect to any potential field. So all this stuff can be lumped together, and we see that the change in energy is just the heat transfer plus a generic work term that I'm throwing in, okay? So that's what we end up with for our energy balance, okay? So very, very simple. Now, we can express this in terms of entropy. For an isothermal process, the heat transfer is equal to the temperature of the system times the change in entropy. And so because the all this stuff here in this part of the equation is zero, we can rearrange everything here. We see that the work done is simply the product of temperature times the change in entropy. So if we can define the change in entropy, then we can calculate the amount of work. Now, one little note I'll make here is that this is a minimum amount of work because we're not accounting for any inefficiencies in the system, heat loss, that sort of thing. Okay, so just remember that the number we get here is going to represent a minimum in an ideal case. Okay, so before we get to the entropy, let's think about doing a mass balance. So if we go back to our system here, we're not creating or destroying any mass in this magic box. So that means that the total number of moles coming in here on the left has to be equal to the sum of the total number of moles coming out the other side, okay? So that allows us to write this expression here. So the incoming flue gas stream in moles per second is balanced by the sum of the exhaust and the capture stream, okay? Now, the other thing is that we're not creating or destroying any CO2, so we can write a CO2 specific mass balance where we simply multiply the mole fraction times the flux. So this is moles of CO2 per second. Now, one thing I'm going to do over here is we'll assume that the capture stream only has CO2 in it. So X capture is equal to 1, so I'm not including it here. But we'll assume that maybe there's some impurity in the exhaust stream. So maybe we're capturing CO2, and there's no impurities in the captured stream, but maybe we're not capturing all the CO2, and some of it goes out in the exhaust stream. Okay, so we end up with this, and we can define a capture efficiency here, which is going to be the ratio of the captured moles to the number of moles coming in the flue gas. And so if for perfect capture, that alpha would be 1, right? But we can also write that the flux of the capture stream can be written in terms of the flue gas incoming stream with this capture efficiency. So that allows us to remove one of the terms in this equation. And through a little bit of algebraic manipulation, we see that the mole fraction in the exhaust stream can be given by the incoming flue gas stream mole fraction and also that capture efficiency. So that's how we can represent how well we're capturing. We don't have to worry about, the other thing that happens here is that all the fluxes have been canceled out. So we don't have to know how fast the gas is coming in. So that makes this a little bit easier. Okay, so we'll take this equation, we'll file it away a little bit. Now let's talk about the entropy in our system. So we have two separate streams coming out of our magic box, right? The exhaust stream and the capture stream. Now we know that we can add the entropies of those two to get the entropy of the combined outgoing gas stream. So we'll add those together. Let's call that S out. So S is our entropy. And the change in entropy is going to be what happens inside that magic box. And so it's going to be S out minus S flue. And we can re-express that in terms of the individual entropies of the exhaust and capture stream. Okay, so that's kind of how we define our system. Now let's get to the nitty-gritty of what that entropy actually is. So Boltzmann-Planck formulation of entropy. Entropy is Boltzmann constant times the natural log of the possible number of configurations of each system. So we can define what that is if we think about doing a perfect separation here. So we go from some mixture of CO2 and other gases to a complete separation where we've got nothing but CO2 and then nothing but the other gases. So let's go back to our yellow and blue molecules. And let's say that the blue molecules are CO2. And let's say that the yellow molecules are everything else. It's probably mostly going to be nitrogen or water vapor, I guess. But that's what we're dealing with. And we will simplify this problem by arranging these molecules on a square lattice, because that will actually allow us to calculate the allowable number of configurations in the system. It's a simple probability problem at this point. Okay, so if I have some number of nitrogen and some number of CO2 molecules on here, where we have different ways of arranging this, we know that the possible configurations on here from probability theory are given by this expression down here. So that's just, the number of possible ways you can arrange two things on a cubic lattice like that. So that's a whole bunch of different configurations, right? These, factorials get large in a hurry. We'll deal with that in a minute. These systems over here, they both are very straightforward. There's only one possible configuration that you can arrange those molecules, because entropy doesn't depend on which specific molecule is in which specific location, right? It just has to do with what that configuration looks like. So there's only one configuration here. There's only one configuration. Okay, so that's pretty straightforward. Obviously, if we didn't have perfect separation, that wouldn't be the case, but we're assuming that now because it makes the math a little bit easier. Okay, now the actual entropies we get by taking the natural log of those configuration numbers and multiplying by Boltzmann's constant. So for the exhaust and capture streams, the entropies are both 0 because there's only one possible configuration. For the incoming flue gas stream, the entropy is some complicated expression involving natural logs and factorials. And the change in entropy is given by this expression here, and it just works out to be that. So we are left with an expression that is probably intractable to calculate because the number of molecules, or even the number of moles of molecules, is probably some large number. And taking the natural log of that gets very difficult. So we can make a couple of simplifying assumptions here by assuming that this is a very large number. And that allows us to make this a tractable problem. So there's a little trick we can do here, where if we take the natural logarithm of a factorial of any number, it turns out that by the laws of natural logs, you can reduce that to the sum of the natural log of each individual number up to that number, okay? And so once we get that, if we have a sufficiently large limit of summation here, we can write this as an integral, and this has solution this, okay? We can actually carry out the integral. And again, assuming that this number x is very large, much larger than 1, we can throw away the 1, and we're left with this expression over here. So that's how we get to that natural log of a very large number involving factorials. And so we can throw this expression back into our entropy expression. And the individual steps in here aren't particularly important. I put them up there in case you're curious. But what we're left with now is an expression for delta S that does not involve factorials, and actually is something that we can calculate as long as we know what these numbers of moles are, okay? So that's what we have. Now we can recast that rather than in terms of absolute number of moles. Let's divide the whole thing, let's divide each of those by the total number of moles, and we can recast this in terms of mole fraction. So if we know what the incoming mole fraction is in the flue gas, we can figure out what the change in entropy is going to be from this expression. Okay, and again, this is only valid for perfect separation, but it allows us to get a number. Okay, so getting back to the fundamental question here, which is how much work does it take to separate the CO2 from the rest of the gases? So remember, the work is simply temperature times change in entropy. So here's our change in entropy term. We're doing this in terms of absolute entropy, but which is incoming flue gas flux times the change in entropy. But we can actually work this out per mole if we divide through by this. So this expression over here, this is the work per mole that we have to apply to the system to separate this concentration of flue gas. And that is how we arrive at that expression. And just to finish up here, we look at the amount of work that's required to separate gases. This is what we end up with. So this is the minimum amount of work that you have to apply to the system as a function of the mole fraction of CO2 in your incoming stream. So if you look at the comparison between this type of gas power plant, it's an integrated gasification combined cycle. This would be where you're actually doing the carbon capture at the point of generation. You can see that your work is on the order of about 3 to 4 kilojoules per mole. If you get up here for doing direct air capture from the ambient air, remember we're at about 420 parts per million right now. That dramatically increases the amount of work that you have to do. And so there is a thermodynamic issue with doing direct air capture, which is that you simply cannot get away from the fact that it just takes a whole lot more work to separate that gas than it does to capture it at its point of generation. Now, there are some ways around this, right? You can probably settle for not doing complete removal of the CO2 in the incoming stream and stuff like that, okay? And that will reduce the amount of work you do, but it also reduces the efficiency of your system. And so, there's a lot of work being done right now on process optimization and material design, that sort of thing, to try to make this end of the carbon capture energy spectrum work better. But as you can see, it's a lot better it's a lot easier to capture the CO2 right from the point of generation. And so I think there's arguments to be made that, maybe that's something we should be doing a lot more of as well. Okay, so that's the baseline for thermodynamics of how we capture the CO2. So a little pessimistic, but if you can scale up the technology and think about where you're getting this energy from, then you can think about that. Okay, so let's set aside direct air capture for now. We'll come back to that and talk about where that energy comes from. If you're running carbon capture on a power plant, the easiest thing to do is to use some of the power plant output as the energy source powering your magic box, okay? And so that introduces these concepts of energy penalty and parasitic energy. So the energy penalty, that's just how much of the power plant output you're putting into your magic box, okay? And then there's additional things you have to do once you capture the CO2. It's basically you have to compress it and move it off-site, and that takes additional energy. So we call that the total energy you're using for separation and compression. That's called the parasitic energy. And just to give you some ideas of what that energy penalty might be. So this would be for a typical natural gas combined cycle power plant. If you are capturing 100% of the CO2 that's coming out of your power plant, depending on how much CO2 is in your flue gas stream, you can be looking at something between 4.5% and 5.5% of the total energy output just being used for the separation. So from an economic standpoint, you have to think about, is that going to make sense for me to do? And if you're not getting any revenue for that CO2 capture, and this is a point we'll come back to later, if you're not getting any revenue for that, you might say, forget it, I'm not going to do this. It's too expensive. I'd rather just sell that energy to somebody else. And so, having some sort of tax incentives or some kind of a market for carbon utilization, that's a really important part economically of making this make sense. And this is, one of the more efficient, options for doing the carbon capture. So that's what we're dealing with. So I think the take-home point of this part of today's lecture is that thermodynamically, there's a huge penalty for trying to capture CO2 with direct air capture. And even on a power plant, if it's easier to capture the CO2, it still requires you to use some energy, and that's lost revenue unless you can make up for that in other ways. So those are the challenges associated with that. Okay, any questions about that? No. Okay, fantastic. All right, so what's in the magic box? How do we actually get the CO2 removed from the flue gas stream? So there's really 3 different technologies that you can use. So one of them is absorption, and the other one is adsorption. And it's really great that they sound so similar, but they're 2 different processes. And then the third process is membrane separation. And this is not used a whole lot for carbon removal, just simply because it requires, high concentrations and high pressure differentials across the membrane. So we're typically not dealing with those types of pressures at the conditions where we're doing carbon capture. So that's kind of a minor thing right now, at least for large-scale industrial deployment at power plants or for direct air capture. You're going to be using mostly the first 2 technologies here. Okay, so let's have a look at how absorption works. So the way this works is we are using some kind of a liquid solvent that preferentially absorbs the carbon dioxide into it. And so we've got the flue gas coming in here to this column, this absorption column here. And this is where you have your solvent, and it's usually at slightly elevated temperature between 40 or 60 degrees Celsius. What comes out here is solvent with the CO2 in it, and it goes through a heat exchanger. Now, the reason why we've got a cold stream and a hot stream here is because absorption and desorption are work differently in terms of heat exchange. So absorption is an endothermic process, and so it requires heat to happen. That's why we are, heating up the absorption column over here. But then the desorption, so what happens is this, when the absorption happens, the solvent gets cooled down. And then it goes through a heat exchanger where it's exchanged with hot solvent that's come out of the stripper column here. So when you desorb the CO2, that is an exothermic process. And the stripper column will be heated up, and you'll have a hot solvent come out of here and come back to the absorption column. So there's a heat exchange process associated with this as well. And so when everything works properly, you'll have about 99% purity CO2 coming out of the stripper column and about 1 to 1.5% CO2 in the treated flue gas. So it's not perfect absorption, but it does pretty well. Now the energy input that you need for this system has to do with the heating of the columns. And there's a little bit of recycling of waste heat that happens in this reboiler too, which might require some energy input to keep it going. So that's where the energy actually goes in to the system here. And again, that's going to be energy that's taken from your power plant that's used to power this cycle. Okay, so this is a really generic system. And there's obviously a whole bunch of different modifications you can make to this if you want. You could have multiple heat exchangers. You could have a more complicated waste heat recycling system. Actually, this is just kind of an aside, but waste heat, if you're thinking about opportunities for, increasing the efficiency of, power generation and energy generation in general, waste heat is a huge opportunity because so much of the inefficiency in electricity generation goes to losses from waste heat. And so figuring out ways to recycle that, in terms of like thermal energy storage or, immediate recycling or that sort of thing, there's a lot of opportunity there. So those of you who are into the more kind of thermodynamic aspects of this, that's something I encourage you to think about because there's a lot of cool stuff you could do. Okay. So the solvents that we're going to use in here, you want it to be able to absorb as much CO2 as possible. We call that the working capacity. We want the heat of absorption to be relatively low to make it easier to absorb. And so we want, this will allow us to have lower water content in the gas that leaves the stripper column and things like that. We want it to react well with the CO2 so it absorbs more easily. We want it to operate at a higher temperature so it can carry more CO2 within it. And also we want it to have a low viscosity because that makes it easier to pump because you have lower frictional losses. Okay, so usually the solvents that we use, they're going to be soluble in water. And so these can include things like sodium or potassium hydroxides. They have, the problem with these is that they have a high heat of absorption. So it's higher to do the separation step when you get to the stripper column. And so typically what's used right now are these aqueous amines. And this is a fairly mature technology at this point. Monoethanol amine is, typically used for this. There are other things you can do with enzymes and that sort of thing, but these aqueous amine solvents are typically what you would use on a power plant. Okay. There's also some research going on right now into what these things called ionic liquids. These are just really large molecules that are liquid at room temperature. And again, they have very good CO2 absorption properties that make them interesting targets for that, but the technology is not as mature right now. So like I said, for doing this on a power plant, amines are probably the way you're going to go. Okay, Now, the way that these things actually work is described by Henry's law. So we've got an incoming gas stream, which is interacting with a liquid-based absorber. And so we have to think about the partitioning of the carbon dioxide between the liquid phase and the gas phase. And that partitioning is given by Henry's law. And so Henry's law just says that if you multiply the mole fraction in the vapor phase times the total pressure of the vapor phase, that'll give you the mole fraction in the liquid phase if you know what Henry's constant is for that system. And that varies as a function of the particular gas you're dealing with and then the composition of the liquid phase. And there's ways of calculating the Henry's constant that y'all probably learned in thermodynamics and we don't need to get into right now. But one of the consequences of Henry's law is that if we plot the concentration in the vapor phase versus the concentration in the liquid phase, it'll fall along a straight line. That's called the equilibrium line. And the slope of that is given by Henry's constant divided by pressure. Okay, so regardless of where you are, if you're operating at equilibrium, you are going to be along this line. All right, now we very rarely are operating in equilibrium. We're usually operating above equilibrium, which allows us to force more CO2 into the liquid phase, because again, that's what we're trying to do with the absorption system. And so the way that these absorption systems work is described by what's called a McCabe field diagram. And this is simply a plot of the partitioning of the mole fraction between the gas phase and the liquid phase. And most of these systems typically have several stages where they operate that kind of step down in terms of pressure. So let's see. So let's imagine we've got an incoming flue gas stream right here. And our operating conditions are given by this line here. So in our first absorption stage, we have no choice but moving from the operating line down to the equilibrium line. You can't go below the equilibrium line. And so that's how much CO2 you can remove from that first operating stage, okay? So it's actually only a very narrow range. So then what you have to do is you change your conditions to get back to the operating line, but now we're at a lower concentration of the flue gas. So then we'll partition that in a second absorber stage. So same thing, we have no choice but to go down to the equilibrium line. And then we'll change our conditions to get back to the operating line. And then we'll have a third absorber stage. And so the amount of CO2 that you can absorb from the incoming flue gas stage, and there's a fourth stage there, it really depends on how you design the system. So what the operating conditions are relative to the equilibrium line. And then the other one is how many stages you want to put into the system, okay? And that becomes just kind of a physical limitation because these things get very large when you're dealing with them on an industrial scale. So even having like 4 or 5 stages, you end up with a unit that's several stories tall for doing the absorption. So there's some limitations. Yeah, question here. Is this the same as the desalination process? Yeah, it's a similar thing because with desalination, you have a kind of maximum separation capacity of the membranes, because that's typically how it's done. So you'll have to go through several stages like that as well. But yeah, I mean, it's analogous to a lot of different industrial purification processes because, most of the time with separations or purification, there's no like magical thing that can completely separate it all at once. There's physical limitations to how these things can operate. Okay, so that's how we do absorption on power plants. Now, you can also do absorption for direct air capture, and this works a little bit differently. And we'll talk specifically about where the energy input is here. So this is what a direct air capture system typically looks like. You've got these fans that pull the air in to what's called a contactor, which is where you have some kind of a sorbent that will soak up the CO2. And so systems that use absorption are going to use these chemicals called aqueous hydroxides. It's usually either sodium or potassium hydroxide. And so the way it works is that the air contactor is over here, and you've got aqueous hydroxide in that contactor. And so that will react with the CO2 to form some kind of a carbonate. And that'll go through a process called causticizing, which mixes this lime with the product of your carbonation reaction. And it allows you to come over here then to this calciner. And what this does is really you can just decompose these carbonate minerals by heating them up. This is exactly the same process to what's done in a lime kiln when you're making Portland cement. So you take calcium carbonate and you heat it up to like 900 degrees Celsius, and it breaks down into CO2 and calcium oxide, otherwise known as lime, which then you hydrate in this the Slaker chamber here, and then it comes back through the causticizer to react again with these carbonated hydroxides that have come through here. So that's the basic way the system works. Now, the two places where energy is required are, first of all, you need electricity to power the fan in the air contactor. So that's pretty straightforward. But the big deal is what happens over here in the calciner. So you need to heat that up to, like I said, about 900 degrees Celsius to decompose that and break off the CO2. And, you know, if you're not careful with this, you know, the easiest way to do this is with a combustion chamber where you're burning natural gas. But then you have to deal with the carbon emissions associated with that as well. So you can try to capture them at the source, or you can use some kind of an alternative fuel source, like burning hydrogen or something like that. But those are the two places where you need energy inputs for this direct air capture system. So this, you know, again, because of the thermodynamics of separation, this is a little bit of a challenge to do. Okay, so we looked at absorption. That is where you're getting an actual chemical reaction with your sorbent, and then you need to separate it off. And basically, the best candidate for this process is going to be separation from point source at a power plant. Okay. So the other technology that's done is adsorption. And the difference between adsorption and absorption is that adsorption is the sticking of the molecules to a surface. And whereas adsorption, the molecules actually go into the sorbent and interact with the sorbent molecules there. So for adsorption, again, we've just got an interface here. So we want to get the CO2 molecules to stick to some kind of an interface when we do this. And there's two ways of doing that. So one is called physisorption, and the other is called chemisorption. So physisorption, we have van der Waals forces that are attracting the molecules to the surface and causing them to stick there. Chemisorption, actually, the molecules go and they interact chemically with the molecules on the surface here, and they form chemical bonds. So either one can work pretty well. What's being investigated right now for direct air capture are what are a lot of physisorbents right now. So zeolite is the big one that's used in a lot of direct air capture systems right now. And this is a metal oxide that's got a regular geometry. And the way it works is that there are certain regions in the crystal lattice here where CO2 can preferentially absorb because of the intermolecular interaction potentials that are here. So this is a molecular dynamics simulation of one particular zeolite. And the color scale here has to do with those, we call them potential wells, right? So it's going to be a spot on the crystal lattice where the interaction potentials are such that the CO2 can adsorb there. So you can design your zeolite such that you have more or fewer of those locations. Another good one is simply activated carbon. So this is charcoal. And this is, it's got a very chemically heterogeneous surface with a lot of places where CO2 can interact with the different functional groups that are sitting out there. So that's another thing you can do. And this is actually, some of you may have heard of soil carbon amendment or biochar. This is a way of sequestering CO2 in the soil, partly through the charcoal itself, but also through the preferential absorption on the surface. And then clays can also work as physisorbents because they have very high surface area. They can have surface complexes here that'll work with the CO2. And so this is another way that you can do it. But zeolite's probably the most efficient of these. And then the other type of sorbents are these chemisorbents. There's a lot of different interesting things that you can do. Anything from a basic metal oxide where you can get just the chemisorption on the surface there. You can take amines and put them on nanoparticles or nanorods, that sort of thing. So you actually, can get these, solid chemisorbents which have amines in them. And then probably the most promising one right now are these metal organic frameworks. There's a lot of work being done right now on these. They're abbreviated as MOFs, M-O-F. A lot of really cool work being done on these because you can design a metal oxide lattice and put some other molecules in here that can encourage the CO2 to preferentially chemisorb on that sorbent. And I think the next couple of years, we're probably going to see some really big breakthroughs in direct air capture technology driven by these advances in metal organic frameworks, because you can really fine tune the way that these things work. So I think that's going to be pretty cool. Okay. I think we have covered enough material at this point in terms of carbon capture that we can call it a day. So thank you all for coming. We'll talk about different separation technologies on Wednesday.